Hi, everyone. Thank you for joining us today. And thank you to our advisory board for being with us. So this week for our internal seminar, we are doing some staff presentations for the advisory board. We'll begin with me and Antonia talking about our multi-sensor core logger coming in at Earl. Dr. William Andrews will talk about state map, and then Dr. Bill Hannenberg will talk about the flooding research in Eastern Kentucky. So with that, we're gonna start.
Does anybody need any lights off to see the presentation better? We good? All right, well, like she said, I'm Antonia, if you haven't met me before, and we're gonna be talking about the MSCL. That's short for the multi-sensor core logging tool that's coming out to Earl in the next coming months. And if y'all didn't know, that's Earl. Ooh, it's clicking here, but it's not clicking there. All right. There we go.
Nope. See, it's moving here, but it's not moving over there.
Oh, that's fun.
That's a new one. What is happening? Sorry, everybody. We figured this out.
Difficulties.
Say, why is it in presentation? It is. It was supposed to be because that's what showed up there. I can't see because Dan. Go from beginning. Now will I do it? No. Where's Mike? Did Mike leave?
Does anybody know where Mike went?
No.
It'll switch here. It won't switch there. So our slides aren't. Like here,
That might be what we do. Oh, did it?
Can I close out of this?
Formatting.
And then where's your here? This is yours.
Yeah.
No, that's true.
See, now let's check.
Last week when it did this, we just opened it in.
No.
So scratch that one, yeah. For some reason, we did like start show, it wouldn't work, and then doing that the other day worked. So try
Now
to
it
see
should
if it'll
work.
tab.
Got it back.
Yeah.
Got it back, y'all.
Thank you, Meredith.
Thank you. Okay, all right. Everybody ready? So this is an MSCLS. This track here is about 15 feet long. And it can hold a core that's roughly anywhere up to 5 foot. And basically there's a roller system right here, which this symbol right here is for the heavy duty pusher. So it's pushing this core on down. And all of these orange dots represent the sensors that you can have on this track. So it's kind of this assembly line of features. And just real quick as a background, I first saw this machine when I was up doing sediment research at the University of Minneapolis, Minnesota. So the Continental Scientific Drilling Facility has this. And I tell you what, I've never wanted a machine more. Like I saw it, I saw what it could do. It was, wow, I need to have this somehow. So we'll just work our way around and kind of introduce everybody to the sensors you can put on. So this one right here, that'll tell you more about your core density and porosity. There's like a small cesium-137 source in there that'll help you do that.
Where's that? I'm sorry, I didn't see the point.
So it's right, it's kind of hard to see this orange line, but it's right there, and that's what that symbol is for. So this camera symbol, if you don't happen to have a wonderful core photographer like Natalie Fields right here, you might need the high definition camera that'll take these lovely photos and keep an even lighting on your core. This one right here is your acoustic velocity. So that is your P wave sensor. And there's also an accompanying S wave sensor you can get. And this one represents your color spectrophotometer. So that is your red, green, blue, and can also give you your Munsell soil color code, which I use a lot when I'm looking at soils. And this right here, that's your magnetic susceptibility. You can get this in a loop and a point sensor. So the loop one is for whole core, and that's another thing that this machine can do. It can do whole cores. Basically, you don't have to split them. You can have them split. And then it can do sediment cores that are split or whole, and they can still be in the original liner. You can have them in their plastic liner and a metal liner. So the loop sensor will actually do the whole core, and the point sensor will do the split core. And this right here is your natural gamma. So that'll look at your potassium, uranium, thorium naturally occurring in your soil sample or your cores.
Is it just a scintillometer?
I'm not quite sure.
Yes. Okay.
Yes, thank you.
It's a spectrometer.
Yes,
It's going to do the radiometrics spectrometer.
yes.
Okay, okay, thanks.
Thank you, Drew. And as we work our way down, this is your electrical resistivity. That's usually good for a core that's already been saturated or in brine. This one right here, which leads up to here, that is basically handheld XRF. So you can get it as a Olympus Vanta, sorry. And that'll tell you more about your chemistry going down through the core. This one right here is your hyperspectral infrared camera. So that'll tell you more about your mineralogy. One example they gave is like you can look at the levels of dolomitation in your limestone as you go through. So there's all of those. Hopefully you're in love with it. It's like getting a little bit in love with it just as much as I am.
On the resistivity, can you do partial core and whole core?
I believe so, yes. Yes. And if you're like me, when you're shopping, you want to know all of the options. So the reason why we picked the MSCLS, all of these are made by the Geotech company in London. And the MSCLS, which is just your standard, it had the natural gamma spectrometry and nothing else did. And then all of these other sensors you're able to add on through time, depending on what your needs are. It only was missing the ultra sensitive XRF and the X-ray CT. So we've gone over the sensors. We've looked at the different options. Why do we need one? Why does KGS need one? So Liz and I really talked to our EES colleagues and our KGS colleagues, and we gathered that a lot of us were working on paleoclimates, limnology, terrestrial geology and soils, petroleum and mineral exploration. So this would come in handy, not just for me for soils, even though I love soils, but for everyone else as well. And over here is just a very simple graphic that is on the Geotech website showing you the rich amount of data that you can get just by simply pushing something through. That's it. That's all you got to do. Just load it, push it through, and you get all of this great data real time, and it's saved in a proprietary, thank you, ASCII file. So that's useful for multiple software programs. So right now I'm going to pass it off to Liz, and she's going to talk to you about which analyses we wanted first and the future of this instrument. Thank you. Let's scoot Monty up here. So like Antonia said, there's obviously a justification for this, but more specifically, this acquisition will help numerous current and proposed externally funded projects in energy, climate, archaeology, civil engineering, and agriculture. And we had representatives of those projects in our recent proposal for so we sent in a proposal to the Energy Research Proprietary Area for UK to purchase this equipment. And we were obviously funded because we're telling you about it. So we talked to our collaborators, tried to match the sensor systems with their needs, but we did give a obvious priority to the, oh, sorry. Yeah, sorry. Maybe. What he said you wish. There, never. Okay, can you hear me? But no. Yes, delayed. Okay, cool. Thank you. So, yeah, for y'all that didn't hear that, the acquisition of this equipment is going to help KGS staff with and our collaborators with several ongoing and proposed projects. We requested funding for this equipment through the UK's Energy Research Priority Area. And so since they're emphasizing in energy, we also tried to emphasize our proposal and our center request for energy research. So some of those projects were hydrogen storage, underground carbon storage, and the characterization of gas shale units. Again, budget constraints did limit what we could request. These are the three systems that we are requesting: the natural gamma, the gamma density and thickness, and the magnetic susceptibility. The hope is that since we were awarded this for the larger purchase of the equipment, hopefully in future years, there will be more research funding for other sensor systems as users come to us. So, yeah, as previously stated, the MSCL has applications for many other research fields, and our collaborators were interested in environmental and geohazards research, as well as an interest in anthropology and civil engineering. I will mention MSCLs are not super common. The closest are Kansas, Minnesota, and Pennsylvania. And so by having one in Kentucky and a routine access to it, that lays the groundwork for more funding opportunities through DOE, USGS, NSF, IMLS, and NOAA for, again, our collaborators and KGS staff. These research activities included in our proposal will provide workforce development opportunities in STEM fields and align with the state's current energy strategy, KYE3, which focuses on environmental development, energy infrastructure, and environmental literacy. So some of you might be asking why Earl? And well, Earl is a research library. We house all of the geological sample collections and associated documents, including almost 3,000 rock cores and over 600 soil cores. It's also, this facility is 48,000 square feet with an analysis room over 4,200 square feet. So it is literally the perfect place for a large piece of analysis equipment like the MSCL. So where are we going to put it? We're going to put it in this space right here in our core viewing room. We picked that spot looking at the space requirements, light and dust requirement, avoidance, IT and electrical needs, and that's kind of our purpose thought in our facility. So all of that in the picture will be scooted out of the way, realigned, and it will be right under those windows. The equipment should arrive in mid-July, at which time geotech staff are going to come set up the equipment for us in that spot. They're going to train a couple of our staff on its use, capabilities, and care, and then we're going to organize some open house events for our potential users. Those users will be KGS staff, UK faculty and students, and then other Earl patrons. Acquiring an MSCL will improve our ability to provide comprehensive data about our samples to our stakeholders and provide KGS staff opportunities to propose innovative and fundable archived science and geoinformatic projects. Possible funding sources for those will be USGS, IMLS, NEH, and NSF. And those potential projects could include elements of data creation, investigation into storage best practices for the purpose of data integrity, and contributing to national conversations on uses-based discovery models. Just like with our collections that are sampled at Earl, users of our MSCL will be expected to share copies of their subsequent publications with KGS and credit Earl samples and staff contributions in their publications and presentations. All of our samples are registered with IGSNs, and in the same way, all of the data that is acquired through the MSCL will be registered with DOIs and disseminated through our website, UK Knowledge, and other larger repositories. The timing of registration and dissemination will, of course, depend on PI publication timelines, and a summary of those PIs and projects benefiting from us having this equipment will be hosted in our annual report. Again, the hope is that by having an MSCL at Earl, it will expand our audience and the survey's collaborative network through innovative research. So. Woo! That's it. Yes, rock cores and soil cores.
That are already in storage.
Correct.
So about the moisture concern, is that? Is there, has that been addressed or considered, or, I mean,
It has been considered.
it's not everything, but
Right.
it just will next summer, so.
It will. So while I was at the whiteboard, we did use staff sheet on fully tracking. And staff grad student really trusted the results and calibrated them. So I'm hoping that the company will talk to us more about that calibration process and how we can deal with different situations. So the big deal with our so.
Okay.
So that's what I'm hoping. Thank you all. Yes.
Explain how.
I do have to go. Oh, yeah, she is CPR training, so she's running, but
Explain, if you would, then, if I took a cord that was pulled from a cord hole that had been geophysically evolved with the same similar tools, have you compared how those two respond, and are they, I would hope, very, very similar, or how much more you get out of this, since it's probably more focused on it? I'm just blabbering, but.
so that is something, no, we have not done that. I don't think there's a lot of documentation associated with that. One of the things that we're talking about doing, this is kind of in line with what you're talking about, these soil cores, setting up a timeline. So when a new core is received, a part of our accession process is photography and running it through the MSCL to collect that data. We plan to do that on the initial time, and then maybe on a monthly, 3 months, 6 months, however, and see if there's any degradation in that data integrity and what we're seeing. We know that will be quicker with soil cores. I'm not sure. There's been some conversations about if that would apply to rock cores. And so it's something for us to kind of investigate, but it would be part of it if we ran a core that we had a geophysical log running it through and comparing, because in theory, yes, that geophysical log that we have is pressure.
Yeah.
Right when that core was produced. So
Yeah.
and see if there's how that kind of lines up. So, okay.
This is a follow-up. It's also marked for the don't count.
Yeah.
It's so much smaller. It's relative counts. Whether it's the absolute same values, it provides a relative.
Thank you.
Okay. I think I've turned the mic off. Is it working? All right.
That'd be great.
All right, press that.
I'm getting no light, so I'm just gonna have to do this the hard way.
Voice recognition.
Yeah.
You're louder than I am too, though.
So we've given these state map updates before, and we're usually updating a project to you, and we are now updating a program to you with less time than usual. And so this is going to be like skipping a stone across water. This is just going to be hitting some of the very high points of what we're doing, trying to give you a sense of where things are going. That's interesting. So first of all, it's important to acknowledge that the geologic mapping section builds upon a really broad base of existing work here at KGS and other staff here at KGS. We do not exist in isolation by any form or fashion. And a lot of the things that we're able to do and do very well are only because of some of the unique resources that are available here in Kentucky and here at KGS. It includes the detailed bedrock geologic mapping, our really extensive GIS and web delivery resources, the decades of petroleum, limestone, coal, water, karst, seismic data, et cetera, that's here. Our university context, where we can reach out to other collaborators. We have the university libraries. We have a lot of those support resources. Our Esri Enterprise license is absolutely essential to what we do. And then KGS has just improved our internal computer infrastructure, and the access and processing capability that gives us makes a lot of what we're able to do possible. This isn't what that is. So we're gonna see how this, well, it's interesting because they're not.
Close out of PowerPoint, reopen it, and go and view on the bottom right. Open it that way instead of the slideshow from the beginning.
Hold on. I'm gonna do it the way I usually do it, and we'll see how that does. Hold on. Okay. There we go. Okay. All right. I'm ignoring this. I'm looking over here. The mapping section uses a team approach. We have a wide range of very intelligent, very talented people in our group, and they each bring different skills and strengths and energies to what we're doing. And so I don't have a lot of names on the rest of the presentation, okay? Because every component of what we do is multiple people interacting with each other, and one person might be directly responsible, but the group helps. And that's very important to what we do. And so everything else I'm going to say through the rest of the presentation is about people and is about the skills that different people bring. Both the people inside our section, Matt, Emily, Antonia, Meredith, Devin, Dibia, Alex, Jason, Steve, but also people outside the section. A wide range of people are bringing their expertise, their advice, their ideas, and bouncing things off of us. And I do want to note that Antonia is going to be with us for one more week. And we, you know, the energy that she has brought to the soil lab and to soil characterization is going to be sorely missed. But I'm specifically supposed to talk about state map project, not just the mapping section. So state map is funded by the USGS National Cooperative Geologic Mapping Program. This is a 4-component program at the USGS. It was established by law in 1992, and our one of our previous directors, Don Haney, was instrumental in getting that enacted. KGS did not engage that program until 96, essentially by agreement, because we were so engaged in setting it up to not directly show a conflict of interest. We let other people get started before we waded in. And once we waded in, we have not looked back. We've been extremely successful in competing for this money. But there is a FedMap component that all just stays inside the USGS. That's for national priority mapping projects, federal lands, that sort of thing. There's an EdMap component, which is for student mapping projects, academic student training kind of projects. There's a national geologic map database that is a repository of a catalog of geologic map products and a source for us to access standards information for geologic mapping. They also run a regular workshop called DMT, Digital Mapping Techniques, which is a place where the practitioners at geologic surveys interact with each other to share ideas and challenges and technology transfer. And then state map is the arguably most productive part of this. The state geological surveys are the only organizations that can receive this funding. And then we have to turn around, we have to do a one-to-one match. We have to show an advisory committee input, and we have to be done in a year or 2 years now. They've given us the option of 2-year performance periods. And then we have to get to the next project. And so there is an enforced productivity to this. And through the state map program, about 1% to 2% of the country gets mapped a year, which doesn't sound like a whole lot until you think about how big the country really is. And there's a lot of mapping and a lot of map coverage that does get done here, but 1% of the country doesn't get it done, doesn't get it finished in less than a century, right? So there's some other components to this. For a long time, state map paid for new mapping or compilations, and that it was fairly limited, fairly traditional, fairly predictable. So a lot of the digital mapping program that's the foundation for our web services was funded through state map. And then as we were digitizing ourselves out of that work, we transitioned back to new superficial geologic mapping around 2003, 2004. And that's what the primary thing we've been doing with this money ever since. But 3 years ago, there was a mandate given to the USGS to finish a nationwide 2D map, nationwide 3D map by the year 2030. And when we're getting stuff done at 1% a year, this was a moonshot ambitious charge to the USGS. And so all of a sudden, there's more money that's being pushed to the mapping program, and a whole lot more conversation about what we actually have to do to move the state of mapping in the nation forward to come anywhere close to that goal. And so suddenly state maps paying for a whole lot of new things. And that's kind of what I'm going to be talking about right now. Now, these slides are some that Matt Massey put together for our State Mapping Advisory Committee. And it just kind of summarizes, well, Kentucky in general is about 40,000 square miles, okay? And in the original USGS mapping program, they specifically mapped about 7,800 square miles of superficial deposits, right? Since 2004, when we've been doing new mapping, we're getting roughly 5 quads a year done, give or take. And that's added up to about 5,500 square miles of new mapping. So total, we've knocked out 11,000 square miles in not quite 20 years, okay? Which makes me feel older than I should when I think about that. But we're looking at a century of work that's still remaining in Kentucky at our current pace. And that's there's a conversation that we're having inside the group right now about using some of the machine learning, some of the automation, some of the LiDAR techniques that individuals in the group are exploring to see if we could come up with some draft maps on a more accelerated pace to help us get a little bit more coverage. But our standard work through state map is producing these new superficial geologic maps. This is an example of the compilation for Hardin County, Kentucky. It was completed summer 2022. And it's pretty traditional field work, or pretty traditional mapping with a few KGS technological flex elements involved, where we use the statewide LiDAR and we try to model ahead of time what the landforms are, get better detail on some of these landform transitions, and then use that information to go do targeted field work and analysis so that we can be as efficient as possible and as targeted as possible in answering the questions we need to make good characterizations of these maps. These maps and the database associated with it involve the lithologies, the rock types, the boundaries, those contacts. It involves various geologic overlays of certain features, which can be related to the sinkholes that people are working on here at KGS, the landslides people are working on here at KGS. It involves depth to bedrock. It involves field work. It involves landform analysis. There are sample descriptions. There's microscopy involved, grain size analyses, and chemistry all being generated. And then we have other data and data interests and analytical interests here at KGS that come to bear as well. So we produce contract reports, GIS data sets, and these information contribute to our web service. Well, that's interesting. Nice. Okay. Now this is not there anymore. All right, let's try this again. Looks very different over here this time. Okay. It's behaving yet again a third different way. I love technology. Where were you, Bill, when you said the actual rocket scientist couldn't run a PowerPoint? When you were visiting NASA, okay. So here we are, yeah. Not a rocket scientist, not doing great with PowerPoint. The new component that came in 2020 with the charge in 2020 was doing 3D, nationwide 3D. And there were people at other institutions that have been doing 3D for decades, literally decades, in Illinois and Alberta, European geological surveys. And we've been watching them for a decade or so and listening to the presentations they made and essentially going, we're not going to make that mistake. We're not going to do that. Ooh, that sounds like a good idea. We'll try that when we get the chance. But there was no funding. And all of a sudden, with this GeoFramework initiative that came in 2020, there were resources, there was funding. And so we have hit the ground very quickly. And some of the things that we recognized as we came into this is that doing proper, good, detailed 3D geology is very time consuming. There's a lot of data review, a lot of correlation, a lot of consideration. The technology changes fast. And so if we're going to dive into this, we're going to be able to do small areas slowly. But we need information for the whole state. And so we tried to find a way to do that quickly. And the applications and the needs of people for 3D exist now and can't wait a decade, certainly can't wait a century. And so our approach was two-pronged. First, we go for the good, not the perfect, the good. We take all this existing data that we can find inside KGS of previous work that people have done in 2 dimensions and pull it into 3D. And we end up with this very robust database of 3-dimensional component information that we can apply very quickly. And that's what I'm about to talk about. And then using the beginnings of that capability, we start to build new capacity, build familiarity with the 3D, learn lessons as we go, and start doing that really detailed, small scale work. And we're doing that too. So we have sort of 2 thrusts that we're going to our 3D all at once. Whatever we do, it's got to be flexible. It's got to be updatable. It's got to be expandable so we can plug more information into it. It has to be accessible and exportable. A lot of 3D software is very specialized and proprietary, and once you work in that software, things don't export out real well. And so we're working in a platform where we can push things into a range of different 3D software. And we anticipate people coming and going in the program, and we anticipate a lot of questions, and some of our stuff will move forward, stop, and have to be set down and then picked up later. And so documenting our processes and our challenges is very important for us. Some of the things that we've gotten pretty quickly, though, because of what we've been able to do, is we have a 3D fault model, a statewide 3-dimensional 1 to 24,000 scale source fault model. It looked like it was going to take a year to a year and a half until the individual staff had a conversation and figured out how to do it in a week. Actually, it's about an afternoon, but some of the polishing took a week because they found the way to automate things inside the technology and make the best of this available information. So we have a basic first draft statewide detailed fault model available because of this innovation. Because of just vacuuming in all the different existing contour type data that we could find for the state, we have over 200 elevation surfaces stored that represent some parts of boundaries within the state. A dozen of those are consistent enough and cover enough area that we can do a statewide model. If you want to use that QR code right now with your phone, try it. And you can look at our statewide 3D data. That QR code got us an invitation to the 6th European workshop on 3D geologic modeling, because other countries can't let you do that. Their stuff is trapped inside their software, and you have to download their viewer, and you have to learn their. And I can just let you go play with it, right? Because we're working in this kind of a relatively open environment for people to use. And then we have some web tools that people can access, where you can go in, you can click any spot in the state, and it's going to make a generalized synthetic borehole for you, or you can draw a line and it'll give you a generalized stratigraphic cross-section for that part of the state, anywhere you want inside Kentucky. The idea with both of those tools is you're going to use it and come tell me what's wrong, right? People are really quick to just send curl emails when things aren't right with the web service. This is what we're looking for here. We want your feedback. We want to know what we can do better with this. And then those are both that best available quick. What can we get into the system? The foundation work, getting down and really starting to take advantage of the depth of the data here at KGS has been looking at the subsurface wells. And so 2021 to 22, we looked at a series of reference wells with the energy section. 22 and 23, we're looking at the Silurian, again, the energy section. We also are doing gamma logs. This project started before the MSCL conversation really got going. And so we have a student employee out at Earl using the handheld gamma to do gamma logs of some of the cores. And then we are funded for next year to look at the Mississippian in Western Kentucky. And so we're doing these sort of targeted postage stamp projects to improve our subsurface knowledge and our subsurface digital understanding of our geology. In terms of things we can contribute to this national geoframework initiative with the 2030 goal is a whole list of different things in 2D and 3D that aren't just a result of the last 2 years of work. These are a result of 40 years of work here at KGS. But they position us to be able to contribute when the national folks figure out what they actually want and they come ask us what they want, we're going to be able to contribute. An additional kind of unexpected component in the state map program is geoheritage. Geoheritage is a really important tool for us to communicate geologic maps and geologic information to the general public. And that's how we use it anyway. It's also related to geologic area preservation, right? So it's sort of the National Park Service is the poster child for geoheritage. And we have a very close ongoing relationship with national park units in the state, Mammoth Cave, Cumberland Gap, et cetera, Camp Nelson. But it's a tool for us for geologic communication, for geologic education, and for longitudinal research, because we can go back to these parks and we have documentation for how those lands have been managed over time. And so if we're trying to understand some environmental change, we have documented context for how to do that. And so working with these geoheritage sites has been and will continue to be important for KGS, but now there's some money for us to really engage with this. And that's been really nice. And the USGS, as a part of this geoframework initiative, is doing a data layer on geoheritage sites. And they're trying to figure out what data attributes and data structures to put in that. And because of our history with data management, data structures, vocabularies, we're part of that conversation.
Sure, have you been able to bring on like federal funded time limited employees to help with this?
All sorts of different, I mean, there's a whole lot of different pieces being thrown at this. So National Park Service people are participating, USGS people are participating. We're invited to participate, other state surveys are engaged. So there's a whole range of different people in this conversation in geoheritage. Yeah. But in the coming years, the project year that starts this September, we've been funded to do a first geoheritage review of we propose to do state parks and just to come up with the language and the data structure for how to, in a geoheritage framework, characterize the state parks. So what's their cultural value, scientific value, educational value, aesthetic value, et cetera.
The reason I asked about that is that do you have enough staff?
No, but they're funding us, which is
So you can bring in people?
Yeah.
Okay,
Yeah.
that's what I was asking.
yeah. And so yeah, that's what we're getting funding to do this, and that's what's unique is it's usually someone like Steve or Ben or I or Doug have a pet park, right, that we like, or we have a relationship with somebody, and somebody reaches out to us and we're like, yeah, sure, I can show up and I can help you with this, and we do what we can before we have to get back to work, right? No, this is going to fund us to participate with some of these sites, and this is a database exercise, and so it's going to be, but it's going to help us build relationships with the individual parks, which then they can go advocate for us to get money, which has been a tool for us to get FEMA funds. It's like we work with the county government and then they go to FEMA and got funds for us to come do FEMA projects for them, et cetera. So this is going to be a springboard for us to leverage extra funds. But between the surficial mapping, the 3D work, and the geoheritage engagement, there's a whole series of recent outcomes or products that are coming out of this work. This slide could be itself 2 hours worth of conversation. We have the digital reports, the data sets, the web tools that are coming out of the mapping. We have a whole spectrum of people doing novel, innovative, aggressive techniques related to the mapping. The LiDAR modeling, the soil lab, the MSCL, geomorphometry, the Esri 3D visualization, the Esri task automation, documentation standardization, all of these different things, and just field work. And how do we collect that data in the field, store it, and transmit it? We're helping with an in-progress thesis in EES on 3D stratigraphic architecture in the Lexington limestone. KGS got authorship on a USGS geoformer fact sheet. We got to be part of the implementation plan workshops. We helped write chapters of ideas about this that got distilled down to a couple sentences in a paragraph and put on this fact sheet. But our voice is being heard. We had invitations in 3D to go to Denver GSA and this European workshop. And then 3 years running, KGS has had active people in these keynote sessions at GSA. And so at Portland, Denver, and then upcoming at Pittsburgh, we've got a role in each of those. And so all of these different activities bundled together underneath State Map are helping keep us in front of people and helping us draw in more resources. So tried to keep it tight, sorry, but that's the State Map project. So questions before I hand over to Dr. Hamlet. Thank you. And it was really hard to get Dr. Hannenberg to sit still in the hat. But you know. Okay. All right, so with that. I'm going to wish you the very best luck in PowerPoint. We don't have slides, right? Is this yours? Yeah. Is this not? That should be weird. I think you need this. I think the battery is dead on there. You're loud enough.
Okay. Well, thank you, everybody. I'm actually the last speaker of the session. And as we were thinking about topics to have that would be useful for the advisory committee, we thought, well, of course, maybe a good summary of the work we've been doing after the Eastern Kentucky floods would be really good. And I asked Jason Dorich if he could put one together, and he said, I'd love to, but I'm gonna be out of town. And I thought, well, Matt worked a lot on landslides, and Matt's out of town today. So I decided, okay, I would just do this and pull it together. So we have, I didn't even count, a long list of authors that have contributed to this work, but it's actually the combined efforts of people working on several different projects related to our overall KGS response to the tragic floods of last summer. So just to give you a little bit of a reminder, and there was a lot of talk about this, and actually I had an entire media interview with one reporter who was interested in this concept of recurrence intervals and what do they mean, and should we even be using that term. But depending on how you plot it, what duration of rain you measure and where you measure the rain, that last summer's July 22 storm popped somewhere in this box. And the main thing about that is it's clearly above the 1,000-year curve. So each of these colored curves represents different recurrence interval. for the particular duration and the intensity of the rain and the values plot there, depending on where exactly you were. So it was, I think, beyond any question, a truly epic storm. And I think if you get to the point of arguing whether it's 1,000-year storm or 1,500-year storm or 2,000-year storm, it was an epic storm in the heaviest part of the rainfall. Not all of Eastern Kentucky experienced this, but in the heaviest, sort of the center of the bullseye, it was in excess of 1,000-year storm. One of the first things I did, actually, as the flooding was going on, was, and I remember I was like sitting at home on a Saturday with my laptop, and I started downloading the USGS streamflow data because we kept hearing reports about how this was worse than anything anybody had ever remembered. You heard words like the 1,000-year rainstorm, which is pretty easy to calculate. And I started thinking about, well, okay, one thing is what actually was the response. So the first thing I did was to download the Whitesburg curve. That doesn't actually show that. Yeah, there should have regression lines going through there. So there should be an S3 line going through there. I'm not sure why it doesn't show up. But I plotted the Whitesburg curve. So here's the historical record that goes back to 1957 in terms of peak annual discharge and the log recurrence interval, which is the arithmetic recurrence interval. And you can see when I first plotted it, 2022 was literally off the charts. And I just made the range of the chart bigger to bring it back on the charts. But without a doubt, it was an extreme event in terms of the record. And I calculated a recurrence interval of 251 years. And we'll come back to it again, because it turns out there are some really interesting aspects to how you might approach calculating the recurrence interval of such an extreme event. And I thought, well, okay, we looked at Whitesburg because there were a lot of stories. That was one of the hardest hit areas. What was happening downstream in Hazard? So I downloaded the data for Hazard, and I had like double check and quadruple check and make sure I'm not using feet instead of meters and cubic meters per second instead of CFS. And even though when you go downstream from Whitesburg to Hazard, the discharge just about doubles from 9830 to 19,600 CFS. The stage increases about 4 feet from 22 to about 26 feet. But when you look at the historical record at Hazard, it only came out to be a 2.6-year flood. And I'm still looking at that because that, to me, that doesn't make sense. But I go over and over and over the numbers, and that's where it plots. The values don't seem inconsistent, but this we need to work some more on to figure out that is actually real, because the discharge increases, the stage increases, just like you think it should going downstream. And then you go down again to Jackson, farther downstream, and as you might expect, the discharge increases to 54,000 CFS. The stage really jumps up to 43 feet, but it only plots out to be a 68-year flood. So it's an interesting relationship that not quite sure what's happening in Hazard, but it looks like the actual recurrence interval, even though the stage is increasing downstream, the discharge is increasing downstream, the recurrence interval is decreasing downstream. So the big question is, well, why is that? And does that tell us anything interesting about the way that river basins respond? One thing I will mention, when I first looked at the Whitesburg curve, I plotted the river stage instead of discharge. We did the same statistics. That's interesting. It's time the regression lines do show up. And if you plot the river stage, you get something like a 600-year recurrence interval. And at one level, you can say, well, okay, we are so far beyond the extreme. It's a multi-100-year event, and there's going to be some imprecision. But one of the things I think we need to look at more is the rating curve. Because if you think about how we measure floods, that every once in a while, the USGS will go out there and they'll actually measure the discharge. They'll take a stream gauge out, and they'll go across and measure the discharge, and they'll measure the stage. And they'll do that repeatedly at different times. And my guess is they don't do it during a 1,000-year flood. Probably not. But they measure it during normal times. They get a range of values, and they develop something called a rating curve. And that way, in the future, you don't actually have to measure the discharge. You just measure the river stage, and you read across and say, okay, this is what the discharge is. And that's all well and good until you get to a really extreme event. My question is, well, how do you extrapolate that outwards? So I made up my own rating curve using the peak annual values for the Whitesburg gauge. And the blue dots are the actual historical values. And then the issue with calculating what the recurrence interval is what what happens way out here when the stage is 22 feet and the discharge is 9,800 CFS, way above what it was before. So if you do a linear extrapolation of this, you get a value about right here. This is the value that the USGS gave when you look at July 28th, 2022. They give you this peak discharge in that stage. If you plot those, this is what you get. So what the USGS uses is sort of a linear extrapolation. But when you look at these curves, they're not straight lines. So the question is, well, how do you extrapolate that? The official approved real hydrologist club method is to use something called a log Pearson type 3 distribution, and you fit this distribution to your data. But like all fitting things, when you're way at the tail end of the data, it's not particularly reliable, and the log Pearson 3 distribution in particular gets kind of flaky when you're extending it this far. So I didn't include that on here, but you can do that. But if you fit a quadratic curve to this data instead of a straight line, you get something very different in terms of the grading curve. So and this is something I'm going to keep working on as I have spare time. I work on it more and more. But I want to understand is the difference between the recurrence interval you calculate for discharge and what you calculate for reverse stage. Is that an artifact of the way the rating curve is constructed and the problem that we're extrapolating way beyond the range of the data to get these values? So I think that's kind of an interesting hydrologic problem to think about because we don't often get data from such extreme events. The other thing I wanted to start looking at is what the downstream effects are, and this relationship we seem to be seeing where the recurrence interval decreases downstream made me start thinking, well, okay, what happens in these headwaters watersheds, these small isolated watersheds? And if there's an intense storm, it might affect that particular watershed if the center of the storm is right over the watershed, but other headwaters watersheds might not be so strongly affected. But then as you move downstream, you're coalescing these drainages and you're getting contributions. So basically, an event that is a big event for any single headwaters watershed may not be such a big event for a mainstream trunk. So I just started like yesterday or maybe the day before. I think it was the day before I started doing this. So this is really, really preliminary stuff, but I started thinking, okay, how might we simulate this? And I took a really simple approach and said, okay, let's have 8 first order streams. So these isolated headwaters watersheds, and they'll each have the identical distribution of peak annual flows over a period of record. And I think I used 1,000 years for this. But you actually know it doesn't matter that much. So each of these watersheds had the same distribution of peak annual flows over a 1,000-year period, but they were totally unsynced. So you could have a really heavy storm in one watershed and nothing in another watershed, or a moderate discharge in one of the other watersheds. And I ran a Monte Carlo simulation for like 1,000 years to generate these. So these are the results I got. So for the first order, I used 8 first order streams that coalesced into 4 second order, that coalesced into 2 third order, and down into 1 fourth order. And the only place I let it rain was in the headwaters drainages. So you can start asking about all these complexities. And yeah, we can eventually improve these, but this was the first estimate. So I said, okay, it rains in the headwaters. It doesn't rain anywhere downstream, and the only effect is the coalescing flow of these drainages. So as you might expect, because over 1,000 years, these first order watersheds have the same distribution, their values are pretty close. You get down to the second order stream, that's interesting, and the third order stream, and the fourth order stream. So as we see, the peak annual discharge increases just due to the consolidation of flows, but also the distribution starts becoming wider and wider and wider. And again, this is something I started working on Wednesday, so we need a lot of work yet. But I think it's an interesting thing to think about how do these systems evolve downstream, and why does what you see maybe in the main stem of the stream differ from what you might see in the watersheds in terms of the recurrence interval.
So if you took that same analysis and did it with stage, could you back out your storage coefficient as that changes going downstream?
Presumably in a year or two. Yeah, I think so, because it's all sort of a simple mass balancing. It's just
Right.
adding it up as you go downstream. So presumably you could. The nice thing about discharge, though, is that's the actual flux. Stage you would need, I think, to probably somehow take into account the cross-sectional area of the channel. So it might be a little bit more difficult,
Right.
but it would be considerably doable. But I think it is an interesting concept that I want to be pursuing, because it does maybe explain why we're seeing this relationship and why 1,000 years, or, you know, in this case, a 251-year flood in Whitesburg might only be a 68-year flood in Jackson. And that, because people are curious, they ask, well, why, you know, how can, isn't a, you know, are we having too many 1,000-year floods? And then you get into the subtleties that the recurrence interval is at the gauge where you measure it. It's not over an entire county, it's not over an entire state. So you can conceivably have different recurrence intervals. And if you're trying to explain this to people who are struggling with the concept of recurrence interval to begin with, the idea that they can actually be different along the same stream is confusing. So I think if we got a simple way to explain and illustrate among simulations, this would be really useful. Matt Crawford led a group that did some really nice work. So the colored map is actually, it's from, I think it's from NOAA. It's radar-based precipitation estimates. And you can see there's almost like a bullseye here over this junction of Perry and Leslie and Clay and Breathitt counties. And they went out with a whole group of people, all the authors on the KGS publication there, and recorded landslides they could see from publicly accessible areas, basically from roads. So they didn't go in people's backyards, they didn't hike up hollers, they cataloged what they could see from roads. And they came up with something like 1,096 new landslides, which is pretty phenomenal. And I think that's important because when the flooding was going on, a lot of us were thinking, but what about the landslides? There must be landslides. Why aren't we hearing about landslides? And I think part of the reason was there was so much attention paid to the floods because they were the obvious thing, that landslides were occurring. They just weren't being noticed. And also a lot of the slides that Matt and the others recorded were debris flows. And unless you're a trained geologist, you may not distinguish between a debris flow and a flood, especially if it's raining hard or it's at night. Because the aftermath of a debris flow will look like a big flood just came down. So the bottom line is we mapped about almost 1,100 new landslides, and we flushed it out, as you can see on in January, a report of investigations, just documenting those that a number of people have found really useful. So I think that was some really nice work by Matt and the whole group that worked on that. Another landslide project just a couple of weeks ago, Matt and Hudson and I were asked by the mayor of Jenkins, Kentucky, which is just a few miles up the road from Whitesburg, almost into Virginia. There's this whole holler here, and there were a number of houses that had suffered landslide damage during the storm. And the mayor asked us out to look at this because there were issues. Some people had received FEMA money, and they were asking, should we put this back into our house or should I move someplace else? And there's one family in particular that since last July has been living in a trailer at the ready-mix concrete plant down the road. So and one house in particular, it was so distorted you couldn't close the doors. And they were asking, and so we looked at the LiDAR. We spent a couple hours in the field. We looked at the LiDAR. We looked at the old non-LiDAR DEMs, and Hudson made a nice difference in that. So you can't see any difference here where we were, because that's kind of a difficult problem to work with those old USGS DEMs and modern LiDAR. There's a whole range of issues. We did see a lot of photographic change from mountaintop removal mining, and it looked like a couple of the houses in particular where there was trouble were actually down in here. And if you look at the contours, and if you go out there and look in the field, it looks like they actually have built these houses on a dormant landslide. There's a fair amount of evidence in the 2011 LiDAR that there were old landslides there. They certainly weren't active then. And we can see this very often. Landslides can just sit there for a long time, and they stop and sort of they're stable because they've come to rest and they're no longer moving, so therefore they're stable. But that doesn't mean during the next huge rainstorm they might not start moving again. And I think that's what happened here, is that if you, and of course, the people had no idea when they built their homes, but the evidence suggests that a couple of those houses were built on the toe of a large, we don't know the exact date, but it's certainly pre-2011 landslide. It was probably pretty old in 2011 or 2010 when the LiDAR was flown, because the indications are kind of subtle, but nonetheless they're there. So it wasn't good news, but it was another one of those situations where people thanked us because at least it was some news and they had some factual basis to begin moving forward. The NSF Rapid Grant was another big undertaking led by Jason. So the NSF Rapid program is to provide funding to allow you to go out and collect perishable samples after a big event like this, with the idea that, for example, if there's a landslide, somebody may bulldoze it away to clear off the driveway. If there's a debris flow covering a road, it will certainly be bulldozed away. Deposits degrade naturally over time. So Jason orchestrated this. It was not a huge, it's like a $50,000 grant. And one of the keys of this program is you're not supposed to be analyzing data. You're not supposed to be modeling data. You're supposed to go out and collect perishable data and use that as the basis for a future proposal. So they did both some water and sediment sampling. They looked for high water marks, and will be eventually submitting a multi-year full NSF proposal. So this is a DEM of the North Fork watershed, and they collected samples, a number of areas, and the course of the North Fork, and they also concentrated on 2 areas. Feature study, the Robinson Forest, and one in Letcher County. The nice thing in the Robinson Forest, they actually have some drainages that have been unaffected by mining and some that have been affected by mining. So we'll be able to start looking at differences in those. And then in Letcher County, there are quite a few mine areas that has good access. So as we move forward, the group is going to focus on those 2 areas. They did collect a lot of water and sediment samples. Here are some of the water quality results just for iron. They have a whole series of maps, but this is what they measured in the field. They estimated discharge and water quality, temperature, conductance, pH and salt oxygen. They brought samples back in the lab, measured anions and metals. They found a number of cases where EPA drinking water standards, and was minimally wasn't drinking water, it was water taken out of streams. A number of cases where they exceeded the EPA drinking water standards, and those are shown in red. And again, the purpose of this study at this point isn't to explain this or analyze it. It's just to collect the data and use it as a basis for future
What
study.
parameters were exceeding?
Sulfate, aluminum, manganese, and iron.
And this is in stream?
Yeah.
Okay.
Yeah. So this isn't coming out people's taps. This was just for
That's
comparison.
what I was like, finished water? Hold on a second.
Yeah.
Okay, good.
And then this was your work, wasn't it? The water affinity part. So yeah, we used some techniques that Ben developed actually at Grand Canyon, and we brought that here to sort of look at clustering of groundwater chemistry families. So the reddish areas on the map show artificial fill, the yellowish green area is fluvium, with outer blue areas are alluvium, and the preliminary classification put it in the 3 geochemistry groups, 1, 2, and 3. And the interesting thing is that the drainage is coming directly off of Pine Mountain, grouped together in a distinct group, and also the sites closest to the large areas of mining related surface disturbance also had their own distinct group that was high in iron and sulfate. I just noticed that in this now. So again, at this point, we're not analyzing and modeling the data, but we're collecting for future use. And then one interesting thing that there you go. I'm not sure that took 2 clicks. We also are getting a really sophisticated surface water modeling package called TUFLO. We had some people here just earlier this week in Lexington from the company. So it's a package of 1D, 2D, and 3D surface modeling routines, and you can do all sorts of things from basic just discharge modeling to sediment transport modeling, in fact, dispersant transport modeling, all kinds of things. And this is the model that we've been putting together. I think, Meredith, did you actually work on that, or is this from? Yeah, so you worked on this too, and we've been getting some help from the software manufacturer to start learning how to use this model. For example, to start classifying the areas, you can see it's gridded. We can cut some cross sections and have measurement points and cross sections to discharge. And ultimately, we want to develop the capability where, using some of this data, for example, from Robinson Forest, we can do the numerical equivalent of a paired watershed study. Because when I talked to the 35 or so reporters who wanted information about the floods, some of them asked about what is Eastern Kentucky like, but after that, the 2 questions just about everyone had answered is due to climate change and how did the mines affect this? And one of the interesting things about the mines is if you look at the peer-reviewed literature, it's very equivocal. And sometimes it says the effect of mining is actually somehow damp. stretch out the hydrograph and flatten it out a little bit. Other times they say it's to make it a flashier. We're thinking hydrograph. I know for sure that none of them are out there doing these studies in 1,000-year rainstorms, so that's the other thing too. Is that if you do a study during a year where you might have a 2-year flood or a 5-year flood, or even just in an average year with no significant flood, how applicable are your results about the effects of flooding when you have a 1,000-year storm? And we don't know the answer to that. I think it's a really important question to ask. I think a lot of people would jump to conclusions and saying, well, of course, it must have been a huge effect because surface mining has impacted such a large proportion of Eastern Kentucky. But I think we really need to have a physically based, fact-based answer that we can explain rather than saying, well, it must have occurred. So that is going to continue on well after I leave, but I think it'll at least be a step towards contributing to that answer that we really don't have a good answer to now. And it's not like we're saying the mining companies are off the hook. We're not saying, yeah, it's their fault. We're saying right now we don't know the answer, but we should have an answer given the importance of the issue in Kentucky. So we're going to be working on that. And that I think is, oh, there's that comes up. So that's all my slides. So if you have any questions, I'll either make up an answer or refer to somebody else. So. Yeah, Ryan.
I was just curious, you mentioned that there were some people who visited their homes and you realized that they were built on during that landslide. During just normal permitting or surveying to build a home, is that something that should have maybe been recognized, or is that not something that they would have seen? I mean, as far as like whoever does construction and things like that.
Well, yeah, so one, it depends when it is. And a lot of these people started settling there around 1900. And then of course, some they build on houses or build new houses. So yeah, 1900, nobody would have been looking. If you were to go out today, the answer is still largely no. It would depend on what the zoning regulation is in that particular county or town, and most places really have none. Some places have steep slope ordinances, where if the slope is say greater than 10 degrees, maybe they'll require you to get a geotechnical investigation before you build.
Very unlikely in a residential.
Yeah,
And that particular, those houses were probably built, I would say, just
Yeah.
what was on that map between 1912 and 1930.
and you could see on the other side of the valley, there were some places where people just cut away the toe of the slope to build a pad to build their house, and they're having very localized problems. Although it is possible to enact ordinances. One thing people cite is the Uniform Building Code, which a lot of places adopt, and then like Kentucky will say, we're referring to the Uniform Building Code, UBC, and there is a chapter in that about grading, and there is a provision in there that's something like, or whatever specific measures local authorities shall require. So they can, a town could, a county could, a state could. Years ago, I worked on a project in Edmonds, Washington, which is along the shoreline of Puget Sound north of Seattle. And it's best known as being the hometown of Rick Steves, the travel guy. But back in the 80s, I think they started having significant landslide problems in a residential area. And they declared a landslide zone and said, well, if you're going to build here, you've got to do like extraordinary investigations and be really careful. You have to have a licensed geotechnical engineer come in. And actually worked really well because they stopped having landslide problems. And then with the advent of LiDAR, they wanted to come up with a new slope map and create and basically enhance what they had. And I remember one of the things I was learning, and I was a LiDAR consultant on this project to a local engineering firm. And a lot of the homeowners who were in the special landslide zone were lobbying to have the zone dissolved. And their reasoning was, which is, this is impeccable, you can't argue with it. They said the landslide problems have stopped. We don't need the zone any longer. And you're thinking or asking maybe rhetorically, like, why do you think the landslide problems have stopped? But their argument was literally, they were going to the city council and said, this is affecting our values because it's attached to our titles. When we sell our house, that it's in a special landslide zone, and landslides have obviously stopped. So we want this landslide zone dissolved. And luckily they didn't, because that would have been a really stupid thing to do. So it can be done, but it takes whatever government body to say it's enough of a problem, we're going to do that. And inevitably, and actually in Cincinnati, there was a USGS economist, Rich Bernkoff, who back when I was there, so in the 80s, did a cost benefit analysis and basically showed that if you could enact not terribly oppressive regulations to require geotechnical investigations in certain areas, the benefit to cost ratio was way above 1. It was 3 or 4 or something like that. So it's easy to demonstrate, but whenever that comes up, there's always an outcry from, say, builders and real estate people, and they'll say, "Oh, this will put housing out of it'll make it unaffordable for the common person." But the really sad thing is, and it happened here too, that very few people realize, and I bet maybe unless you talk to me a lot, maybe a lot of you don't realize that your homeowners insurance policy excludes any kind of earth movement. So expansive soils, collapsible soils, sinkholes, landslides, anything that's related to moving of the earth, if you call State Farm or Allstate or whoever you have and say, "Hey, I just had this landslide that ran into my house," or "my house," they'll say, "Hey, we're really sorry and good luck with that." Because on like page 147 of your policy, in the fine print right after nuclear war and acts of civil disturbance is the earth movement exclusion. And every standard residential policy I know of has that. So you can say, yeah, this is going to make it more expensive, and it may by 1% or so, but the consequences are, if something happens, you have no recourse except to look for somebody to sue. So you can sue the developer if you can still find the developer. You can sue the engineer, you can maybe sue the real estate, but you can't go to your insurance company because they'll just say, "Sorry, we read the exclusions." So you can make the argument that it's probably worth it to have those zones and those investigations before you build, because it gives you that peace of mind that at least somebody's looked at it, versus waiting for something to happen. And in like 30 years of doing this, like nobody has ever known when they've had a landslide problem. It's always a really tragic shock. And it's like, when's the last time you want to learn that your insurance isn't covering something? It's like when your house, like your single biggest purchase ever, is falling apart. And then you learn about it when you call the insurance agent. So,
And, I would say this, having been in that insurance industry, a good insurance agent should tell you this when you're selling your home, or if she's selling your home. It's something they should advise, particularly if you live in a place like Jenkins at the bottom of the like Jenkins, right? Yeah, you kind of got to be your own advocate these days with healthcare and things like this. You got to ask all the questions yourself. GM spent how much money on the Corvette? And they obviously didn't do adequate geotechnical evaluation. Because a few years after they installed it, it collapsed into a sinkhole.
yeah. Although,
The sinkhole didn't just occur there, it was there, right?
a lot of areas like Jenkins, though, homes might be passed on from generation to generation. They might be cash purchases, they might be paid off.
A
So
lot of them were company homes that were actually built by coal companies when they came up there. I mean, that main road in Jenkins is all company housing.
Yeah.
It was all coal company, coal town.
yeah, and this one, I don't know if it's Improvement Drive, which sounds like a coal company kind of thing. And there was an improvement drive, then improvement loop goes off of it. So yeah, they had no control. And if you're not getting a mortgage, maybe the mortgage company would apply more scrutiny. But if this house was built, it was in the family, it's passed down and it's generation to generation, you may never learn that. And at least if it's a real estate transaction involving the agent, then yeah, a good agent probably should. But one of the things I find interesting as a geologist is I've moved around the country. Like when my wife and I were looking for a house in the Seattle area, and I wouldn't tell the real estate agent what I did. And I would just say, they seem to have a lot of landslides around here. Are landslides a concern? And I would just listen to what they said. And amazingly, apparently landslides aren't a problem in the Seattle area, or at least on this lot. And when I moved here, it was sort of the same thing. They called and asked if I wanted an earthquake endorsement on the insurance, because unbeknownst to me, apparently there's an active fault line that runs right through Lexington.
So Bill, is there, FEMA has the floodplain mapping program. I'm not aware of any other federal hazard mapping program like that where mortgage lenders will seek out information from that, such as liquefaction mapping or landslide mapping. Are you aware of anything?
NEHRP So the USGS NEGR program has funded liquefaction maps for a lot of areas. So those are available for some areas, especially in the western US. Landslides are trickier. There's actually consultant Jeff Keaton, who I've known for 30 some years. He's in Arizona, and he's actually worked with actuaries and had sessions, GSA meetings, and talked about what would you need. And in fact, that article I talked about by Austin Gaffney and Martha Park, they did a really good job, and they actually talked to me and they talked to Jeff Keaton about landslide insurance. And one of the issues about any kind of insurance is that you have to sell it to a lot of people who don't need it. Right, like even car insurance. The only reason it works is because there are a lot of people paying for it who are never going to use it. So with landslide insurance, you would have to be, one, have enough information that an insurance company would be comfortable enough making an actuarial business decision that they were insuring enough people in flat, featureless areas that were never going to need this insurance to pay for the multi-million-dollar houses in California or in Vail or someplace that are going to be subjected to landslides or in Eastern Kentucky. So people have thought about that for a long time. But yeah, in the end, and maybe the National Landslide Preparedness Act will help with that as it continues over the years. But right now, if you talk to an actuary, they say, well, we just don't have the kind of information we need to make like a landslide map of Kentucky that we can use as the basis for insurance. One approach, I don't know if any of you ever knew Jerry Skees, who used to teach here in ag economics. And he's been retired, at least since I've been here, but he's involved with a company called Global Parametrics that's based in London. And they have a different kind of insurance model, and they work especially in a lot of developing countries. And parametric insurance means whatever it is you're worried about, like earthquakes, landslides, flooding, that instead of waiting for the event to happen and sending an adjuster out to say, oh, you get this much and you get that much, and that they'll work with, say, an entire government. And if there is a major earthquake, they'll use really sophisticated models and figure out what the damage was, and they'll just like distribute the money, and they'll say, here, based on where you live and the results of this map, you get this much money without worrying about all the hassle of doing the adjustment. And they have done a little bit of work with landslides in South America using threshold rainfall models, where if you get a certain heavy storm, they can anticipate in an area where there's one of these models developed, you'll have 100 landslides or 1,000 landslides. And then if the government is working with this kind of insurance, whatever government entity it is, will get X amount of money from the insurance policy to use for reconstruction and rescue and everything else. So it's a different way of thinking about insurance that would rely heavily on things like adequate maps or adequate process-based models or statistical models. And each of those have their flaws and weaknesses, but at least it's an approach. But the landslide insurance problem, yeah, landslideologists, we've been talking about that for like decades, like why it is actuarially so difficult to come up with a financially viable way to have landslide insurance. Anything else? Okay, we're all dismissed. Have a good Friday.